I just finished writing your homework as in just right now. I will post that as soon as class is done, just after I proofread it one more time, make sure everything looks good. Keep going with the Alex. Your module for intro to inverse function should have been due last night. And so now the one just for inverse functions should be open. Again, we are done explicitly covering inverse functions. So everything you need to know for both of those homeworks, you should know already from class on Monday and Tuesday. We will be using inverse functions for what we're doing today, but in terms of learning how they work, solving equations with them, we're done there. Today, we're going to be focusing on solving triangles when we don't have right triangles. We're going to be talking about, okay, we know what to do when there's a 90-degree angle. We know we can use trig ratios, but what about when we don't have that? Can we still use trig? How does that work, etc.? So that's what we're going to be focusing on today. And so that, a little bit of that, and then inverse functions will be what is on the homework. Any questions on anything? All right, if there's no questions, we will just go ahead and get started then. Oh, wrong thing. Start broadcast. Okay. So like I mentioned, pretty much this entire semester, we have been using sine, cosine, tangent, etc. when we need to solve right triangles. Like when we're solving an equation and need to find, okay, I know my hypotenuse is 5 and my adjacent side is 3, but I want to find the sine. How do I find the opposite side? Or just solving equations. Sometimes you need to solve a right triangle in order to get one of the missing side lengths, to get all the pieces. Pretty much every single thing we've done in this class has involved right triangles and needing to solve them to complete our problems. However, what do we do if we don't have a right triangle? So the question for today is, how do we solve non-right triangles? And what I mean by the word solve is, given any triangle, how do you find A, not only its side lengths, which we will no longer be able to use the Pythagorean theorem for, but B, how can we find its angle measures? And there's a few different ways we do that. And one of the ways, and the most intuitive, I would say, usable formula is called the law of sines. And it's called the law of sines because, well, it pertains to using sines of different angles. So here's an arbitrary triangle here, ABC. The only thing important to note about it, not the shape or anything, just note that angle B will always be opposite of side B. So side B will never be touching angle B. Side A will always be opposite of angle A. So side A will never be touching angle A. And side C will always be opposite of angle C. So side C is never touching angle C. That is the only important thing of construction, because when we're solving these problems, I will give you the problems in terms of, okay, here's the length of side C and the measure of angle B, et cetera, et cetera. Just know that angle B is always opposite side B, angle A is always opposite side A, and angle C is always opposite side C. Cool. All right, and given that, we have this ratio called the law of sines, where the sine of A over the length of side A is equal to the sine of B over the length of side B is equal to the sine of C over the length of side C. So, for example, if we knew maybe the angle A, side A, and side B, we would be able to use those three pieces of information in order to solve for angle B. Or if we knew maybe angle A, or angle and side A, and then angle C, we would be able to solve for side C. So this is useful when we know an opposing pair of an opposite side angle pair. So what I mean is, if we knew angle A and side A, or angle B and side B, or angle C and side C, the law of sines is a really good tool to use. Note also that sometimes it is much easier, because these are ratios, we can just flip them upside down and write this the same way. So this equation is also equivalent to saying side A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C. And you should believe me that that's true. All I did was invert all three sides of the equation, just flipped them upside down, just flipped the ratios upside down. It's kind of like saying how 4 over 5 is equal to 8 over 10 just as 5 over 4 is equal to 10 over 8. In math, we can always just flip fractions upside down like that, invert both sides of an equation. Same thing, that's all I did here. Sometimes it's just easier to use that form so you don't have an unknown in the denominator, but either form will work. You'll see either one come up, just know that either one is true. That'll be useful too when you're working through ALEKS, and it might give you this as a guide for what to do. And you're like, huh, that's not the law of sines. It actually is. So in order to use the law of sines, we need at least one angle side opposite pair. Let's see what that looks like. So problem type 1, this is called an angle side triangle. And that is because consecutively kind of walking around the triangle, we have a known angle, and then a known side. That's why it's called AAS, angle side. We'll see 6 different types of triangles today. And at the end, I'll kind of classify all of them and talk more about what they are. But just know this is called an AAS because we have 2 angles that we know in a row followed by a known side. The order that that's written in does matter. So I want to solve this triangle. And again, what do I mean by solve the triangle? I want to find the values of all angles and all sides. So I know angle A and angle B, and I know side A. So what I'm trying to solve for is side B, which is opposite of angle B. So that is side B right there. I want angle C because that is unknown. And I also need side C. So those are the 3 things I'm trying to solve for. There's 2 things we could do right away here. But I think I'm going to start with the law of sines, and I'll explain why in a minute. But if we see law of sines here, we have angle A is known and side A is known. So we can use law of sines because we know an opposing side angle pair. Let's see how that works out. So from this page back here, I see that the sine of A over A is equal to sine of B over B equals sine of C over C. I know angle A, side A, and angle B. So I'm going to use sine of A over A is equal to sine of B over B. Plugging our known values in for those, we know that the sine of 120 degrees over 7, because those are the corresponding side angle pair, is equal to the sine of angle B, which we know B is 45 degrees, over, we're trying to solve for side B. We don't know what side B is yet, but that's what we're trying to solve for. You can use your calculator for these problems. That is always allowed because I'm going to want answers in degrees when it comes to angle measure, but I know the sine of 120 and the sine of 45 off the top of my head, so I'm just going to write those out. So this is the same as root 3 over 2 divided by 7 is equal to the sine of 45 degrees is root 2 over B. Cross multiplying like this, if you remember, we can do that with fractions, just multiply in an X fashion like that, just saves us a step or 2. We get that root 3 over 2B is equal to 7 root 2 over 2. So B is equal to, dividing both sides by root 3 over 2, 7 root 2 over the square root of 3. But I don't like that ugly square root of 3 in my denominator, so I'm going to rationalize to be 7 root 2 root 3 over 3, which is the same as 7 root 6 over 3. Cool, there's my side B. I know that B is equal to 7 root 6 over 3. Beautiful. Okay, now I have my side A, side B. I'm also going to use the law of sines to solve for side C because we still know our opposing angle side pair. We still know angle A and side A, but we don't know angle C or side C. Shoot, so all we have right now is sine of 120 degrees over 7 equals sine of angle C over side C. We don't know either of those. So are we stuck? Are we done? What do we do? Well, we're not stuck. We can't figure out side length of C yet because we don't have the information to do that. We can't apply the Pythagorean theorem because this is not a right triangle. However, we can use a very important fact of triangles here. that angle A plus angle B plus angle C has to add up to 180 degrees. Always, always, always. The three angle measures in a triangle must add up to 180 degrees. We can use that fact here because we know the measure of angle A and we know the measure of angle B. We have an equation with an unknown, we can solve for C. So substituting A and B in, we get that 120 degrees plus 45 degrees plus C is equal to 180. And then subtracting 120 and 45 from both sides, we get that C is equal to 15 degrees. So this right here is 15 degrees. Cool. Now we're almost done, and now we can use the law of sines to solve for side C because we now know angle C. Cool. So going forward with this equation above, we can replace the sine of C here with sine of 15 degrees. Multiplying this out and solving for C, we get that root 3 over 2C is equal to 7 sine 15 degrees, just multiplying like that. And then solving for C, C is equal to 14 times the sine of 15 degrees all over square root of 3, which normally I would rationalize this denominator, but I'm not asking for an exact answer here. I want you to plug this into your calculator to get an actual numerical approximation because this number, quite frankly, means nothing to anyone. So plugging this into my calculator in degree mode, make sure you put your calculator in degree mode for when we're working with triangles like this, we get 2.092. And that is it for this one. I have solved this triangle. I have found, first, I used the law of sines to solve for my missing side length B. And then I said, hey, I want to use the law of sines again, but I can't. So I need to solve for my missing angle C, or that's not angle C down here to get that measure, which I can then apply to the law of sines to get my final side length. Questions on this one? This will be the procedure you will use for all angle side triangles, and we'll talk about that more later, just using the law of sines, solving for that missing angle, and using the law of sines again. All right, let's try a different kind of triangle called an angle side angle triangle. And basically what that means, here's an arbitrary triangle. That would mean I would know, say, this angle here, this side length here, and this angle here, or this angle here, this side here, and this angle here. So angle side angles, you will know two of the angles and you will know the length of the side that connects them. So this is a word problem. Sasquatch Island lies off the coast of Ipitzuti Lake. I think that's how you pronounce it. Two sidings taking 5 miles apart are made to the island. The angle between the shore and the island at the first observation point is 30 degrees. So this right here is our first observation point. Just reading the problem. And the second point, and at the second point, the angle is 45 degrees. So here's the shore, that angle is 45 degrees. So this is the second observation point. Assuming a straight coastline, find the distance from the second observation point to the island. So first of all, what value am I trying to find? I want the distance from second observation point, which I identified to be right here, to Sasquatch Island, so here. So what I'm looking for is this side length right here. This is the unknown that is my eventual end goal to solve for. How can I get there? Well, turns out I don't even quite have an angle side angle triangle yet. I know this angle and I know this side, but I don't know this angle right here. However, I have the tools I need to solve for it. If you recall, when we have two angles like this, who we know the measure of this one and the measure of this one, these are called supplementary angles, and their measure adds up to 180 degrees. So we don't know the measure of this guy right here, but we do know the measure of its supplementary angle because we're assuming that shoreline is flat. So we can solve for what that missing angle is, and that missing angle is C. So just doing that, we get that C is equal to 180 minus 45 degrees because they're supplementary. So 135 degrees. Okay, cool. Now we have an angle side angle triangle to work with. We know the measure of two angles and the side length between them. Cool. So now how do we solve for side A? Well, do I have an opposite angle side pair yet? I know down here this is side B, but I don't know angle B up here. I know angle C down here, but I don't know side C. And I know angle A, but I don't know side A. Side A is what I'm trying to find. So I can't even use the law of sines yet. So before I can even use the law of sines, I have to find some other information. I know two of the angles. I know that A is 30 degrees and C is 135 degrees. So I can solve for angle B, and then maybe I can use the law of sines. So doing that, I know that angle A, which is 30 degrees, plus B, plus angle C, which is 135 degrees, is equal to 180 degrees because the angle sums of all triangles must sum to 180. That's just the law. That's just how math works. So solving for B, subtracting 30 and 135 from both sides, I get that B is equal to 15 degrees. Again, not the piece of information that the problem asked us to solve for, but it's a piece of information we need in order to solve, in order to get the answer. So I think we can use the law of sines now because we have an opposing angle side pair. We know that angle B is 15 degrees, and we know that side B is 5. Let's set that up. So we know angle B is 15 degrees. We know side B is 5 miles. Now, what are we trying to solve for? We want side A. So we know angle A, which means we can use the law of sines now to solve for side A. So angle A is 30 degrees, and we don't know side A. Now we can just solve for A. Cross multiplying, we get that A times the sine of 15 degrees is equal to 5 sine 30. Therefore, A is equal to 5 sine 30 degrees all over the sine of 15 degrees, which when we plug that into our calculators, because we're allowed to use our calculators for these because we're not always going to have friendly angles we're working with. Like, for example, I don't know what the heck the sine of 15 degrees is. We get 9.66. And remember, our side lengths are measured in miles, so we need to include a unit there. Questions on this one? Again, this did not require us solving the entire triangle. We still have no idea what the heck side C is, but I bet you that we could use the law of sines to solve for side C if we needed to. But we just needed side A, so we're good to stop here. Okay, let's talk about two other kinds of triangles now, called side angle side and side side side. So we want to see if we can solve these with the law of sines. To do that, I think, again, if you have not learned in this class yet, drawing a picture is always, always, always the best first step to do. So that's what I'm going to do. Just to have for myself for reference, I'm going to draw a generic triangle with its opposite angles and sides labeled, just so I have something to reference when I'm sketching these particular scenarios out. So let me start with the side angle side scenario. Based on my generic triangle, what is that going to look like? Well, I know the angle C is equal to 30 degrees. Again, this is not to scale. I know that side A is equal to 2, and side B is equal to 3. Okay, what can I do here? I can't solve for any of the remaining angles because right now all I have is that 180 degrees is equal to A plus B plus 30. And if you remember from algebra, we cannot solve a system of one equation with two unknowns. We can't do that. We can't look at an equation that has both a x and a y unknown and find x and y. We can't do that. So that's a no-go. What about the law of sines? Well, the only angle we know is the 30-degree angle. So let's try. and that's opposing side is C. So I know that the sine of 30 degrees over C is equal to, I know side A, but I don't know its opposing angle, so that would just be sine of A over 2. And then I know the side length B here, it's 3, but I don't know angle B. Again, I have too many unknowns here. There is no way to set up the law of sines so that I can solve this triangle. So actually, we cannot solve side angle side triangles with the law of sines. Okay, what about this guy, side, side, side? That just means we know the length of all three sides. That's all we know. We don't know what the angles are, but we know the lengths of all three sides of the triangle. So what does this one in particular look like? Well, oopsies. Looks something like this, where we have side B being 7, side A being 4, and side C being 5. Okay, we clearly can't solve for any of the measures of the angles from this because we need 2 of them and we don't have any of them. And also notice there's no way to set up the law of sines so that we can solve this because we know that the sine of A over 4 equals the sine of B over 7 equals the sine of C over 5. Cool. There are no 2 of these we could pick out that only have one unknown because we don't know any of the angles. So what do we do? Well, luckily, like when we were doing the trig identities in the last unit, there's more than one way to do these. There's more than one identity. And that is something called the law of cosines. Again, it's kind of a derivation of the Pythagorean theorem, because if you remember, a squared plus b squared equals c squared. However, because we are not working with right triangles, we now have this adjustment term out here. We have 3 different forms of this, and all it is just relabeling things. Just instead of c squared here, we used a squared, and we had the cosine of a instead of the cosine of c. And so all that these 3 different forms are is just relabelings of one another, which we're allowed to do now, right? It's not like a right triangle where one of the values has to be the hypotenuse because it's the hypotenuse and the other 2 are fixed as the shorter side lengths. That's not how this works. We can use any 3 of these forms on any non-right triangle we want. So the general form is this. I find it, again, this is a little bit of a weird formula. I think it's easiest to remember that we're always finding the cosine of the angle with the corresponding side length over here. And these two side lengths are right there. Again, you don't have to memorize these. We're not going to derive why they work in class. Just know that if we have any 3 of these pieces of information, like for example, if we have all 3 sides, or if we know 2 sides and an angle, that this will be what we use instead of the law of sines, at least to start. So, as we may have been able to tell from the previous slide, the law of cosines must be used as the first step when solving side angle side and side 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 triangles. So because, like, for example, side 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 triangles, we know 3 side lengths, we could plug all 3 side lengths in there and then solve for any of the 3 angles we wanted to. Similarly, side angle side, we'll know 2 sides and an angle. We can solve for the remaining side. And we know it'll be like this because the way a triangle is set up, we'll know for side angle sides, we'll know 2 angles. Oh, I wrote that backwards. 2 angles, and then the side length between them. So we'll know, oh, that's not a side angle side. Wow. Thank you, Sydney. Good job. That is an angle side angle, my bad. We'll know 2 side lengths and the angle between them, and the angle between them will always be the opposing angle. So you'll know those 2 sides and then the opposite angle from the side we don't know. So this will always, always, always be the first step when we are solving side angle side and side 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 triangles. So let's try some examples of that and see what that looks like. Here's a side angle side. I want to solve the triangle with these measurements. Now, let me draw that out just because it's really nice to have a visual when we're working with these, and a visual will actually be kind of necessary later. So I have this triangle here. I'll call this B. We know that's equal to 3. We know A, we know it's equal to 2. We have angle C here, and then angle B, angle A. Cool. It's about what our triangle looks like. Like I talked about on the last slide, we cannot yet solve for any of the measures of the angles, nor can we solve for the third side using the law of sines. So we're going to need to use the law of cosines in order to solve for our remaining side lengths, so we can then use the law of sines. So what I'm going to target is I'm going to try to find side C. So then we can have an opposing angle side pair. So we are then able to use the law of sines. Which of these formulas gives me a known of side C, a known of side A, and a known of side B? And then we solve for side C. The form that looks like C squared equals A squared plus B squared minus 2AB cosine C. We know A, we know B, we know big angle C. Let's plug those in and solve for C. So C squared is equal to 2 squared plus 3 squared minus 2 times 2 times 3 cosine of 30 degrees. Beautiful. Solving that, we get that C squared is equal to 4 plus 9, 2 squared and 3 squared, minus 12, which is 2 times 2 times 3, times the cosine of 30, which is root 3 over 2. So C squared equals 13 minus 6 root 3, which then, taking square root of both sides, C is equal to the square root of 13 minus 6 root 3. Again, when we take that square root, we have to think, oh, is it plus or minus the square root of 13 minus 6 root 3? When we're working with triangles, it will always be the positive version of that, because we cannot have a triangle, like a tangible triangle with a negative side length. So it will always just be the positive version of the square root, which, plugging this into my calculator, gives me approximately 1.615. Cool. I now know my side length C. Now that I have this, I am able to use the law of sines to start solving for other stuff. So my known side angle pair is, I know that the sine of 30 degrees over the side length C, which is really gnarly, 13 minus 6 square root of 3. I can now solve for either angle A or angle B, whichever I choose. I am going to go after angle A first, just because why not? I could go after either. It doesn't matter at this point, but I know I have to use the law of sines to find one of those angles. So I'm going to do angle A. I know that the sine of angle A over 2. Solving this out, I know that the sine of A is equal to 1 over square root of 13 minus 6 square root of 3. So what do I do now to get A by itself? Well, again, when we were solving these kinds of equations in our previous unit, we would think, okay, what angle on my unit circle has a y coordinate of 1 over the square root of 13 minus 6 root 3? There isn't a nice one that we know of, because it's an ugly number. So what have we learned now? We need to use our inverse sine function. So taking the arc sine of both sides, I get that A is equal to arc sine, or sine inverse, that's the other way we'd write it, of 1 over square root 13 minus 6 root 3. Cool. And plugging this into my calculator, because we're not doing this by hand, I get that this is about 38 degrees. Okay, this should raise some red flags right here. Not the 38 degrees, but the fact that we only got one answer. Remember, we are trying to find an angle A whose y coordinate on the unit circle is this guy. We don't exactly know what that number is. However, we do know it's positive, and we know that for positive y values, the inverse sine function is defined in quadrant 1. So we know that 38 degrees, it's about right here. Not quite, it's close enough. But we also know, on the other hand, that this angle has that exact same sign over here. And remember, how we solve for that angle is, let's call this here angle A. This could also be This is also angle A, but they have the same reference angle. So this is the same as angle A. So we get this other angle. Let's call it that A1. Let's call this A2 by taking 180 minus angle A minus that reference angle, which is 38 degrees, and get 142 degrees. So right now we technically have two possibilities for angle A. One of these actually does not work, and I will explain why in a minute. But first, let's follow through with these two ideas for what angle A could be and see what happens. So we have two possibilities for angle A. We know angle C for sure. Let's solve for angle B. How do we do that? Well, we don't even need to use law of sines or law of cosines. We can just sum to 180 because we have two of the angle measures. So B1 is equal to 180 degrees minus 30 minus 38 degrees, since A plus B plus C is equal to 180, and that gets us 112 degrees. B2 is equal to 180 degrees minus 30 degrees minus our other possibility for A, which is 142 degrees, which is 8 degrees. Okay, now which one of these is the real answer? Technically, if I was just asking you to solve an equation, these are both solutions. However, with the geometry, it doesn't work that way, and here's why. So let's very, very carefully try to sketch at least a little bit to scale what this triangle looks like. So this here is my side A, and here is my side B. That did not cross right there. Just a little bit longer, and here's my 30-degree-ish angle. So these side lengths are determined. We can't move them around, and that 30-degree angle is also fixed. We can't move it around. The first thing I did was solve for side C, which I know side C is about 1.615. How many different ways are there for me to fit side C at its scale in this triangle? I know I can do it like this, where they touch both ends. I need the two ends of side C to touch angle A and angle B. Like shown up here, I need that to happen. But is there more than one way to do that? Oopsies. Is there more than one way to do that? No, we can't tilt it any more one way or the other, because if I tilt it more this way, it will no longer intersect that angle. And if I tilt it this way, it will no longer intersect that angle. There's only one way to fit our side C in that triangle in order to make it a complete closed triangle. So there's only one solution. And now the only way, unfortunately, to determine which solution geometrically works is to draw a somewhat to scale picture and look at it. So up here is angle A. Does it make more sense that A would be 38 degrees or that A would be 142 degrees? Well, we know 142 degrees looks something like this, and 38 degrees looks something like this. 38 degrees is acute, 142 is obtuse. A is clearly not 142 degrees. So the only solution that makes sense is that A equals 38 degrees, and then the respective measure for B is that B is 112 degrees. You could have also looked at angle B right here. That is clearly not even close to an 8-degree angle. Is my picture entirely to scale? No, but did I get the ratios at least within the ballpark in my drawing to be able to determine, okay, am I looking at an obtuse 112-degree angle, or am I looking at an 8-degree angle that's like this? So your drawing should be to scale enough just to be able to tell that. These side angle side problems will only ever have one solution. You will algebraically be given two, and you will have to draw a triangle in order to determine which one makes more sense. Questions on this problem? You'll get a lot more examples with these later on, and in ALEKS 2, there's also one on the homework. So Just keep that idea in mind. You will algebraically be given two solutions, but side angle side, there will only ever be one solution that works. And the reason for this is because all three sides, all the lengths of the sides are determined before the angles. So even though we don't know side C right off the bat, side C is the first thing we solve for. There's only one solution for side C, and we already know sides A and B. So once we have, if you think about, once we have the sides of our triangles fixed, if you take any triangle, you can stretch it or shrink the sides, but it will never change the measures of the angles. There will be no way to bend that triangle around in order to change the measures of the angles. And that is because the sides are determined before the angles are. We will see examples later where we do not determine the sides first, and that leads to some complications. However, side angle side, when we have it given like that, there will only ever be one solution, but you will need to figure out which one it is. All right, now let's try a side-side-side triangle, that other kind of triangle that did not immediately work with the law of sines. So I want to solve the triangle with these measurements for the three different side lengths. I'm a visual learner. It's always helpful to sketch these out, so let's do that really quickly. Again, not entirely to scale, but close enough. 5, 7, 4. Here's angle B, angle A, and angle C. C is opposite from the 5, B is opposite from the 7, A is opposite from the 4. Neat, we're good to go there. Okay, so we obviously cannot use the law of sines because we don't know any of the measures of the angles, and we need an opposite angle side pair in order to use the law of sines. So instead, I'm going to use the law of cosines. And it honestly does not matter which form we use to start this time, because we know all of the sides and none of the angles. So no matter what we do, we will get an opposite angle side pair. I'm just going to solve for angle C again to start, because why not? In other words, I'm going to use the form c squared equals a squared plus b squared plus 2ab cosine c. Plugging in my three side lengths, this means that 5 squared equals 4 squared plus 7 squared plus 2 times 4 times 7 cosine c. Doing some arithmetic, that means that 25 is equal to 4 squared 16 plus 7 squared 49 plus 2 times 4 times 7 is 56 cosine c. Now I want to get cosine c by itself. So I subtract my 16 and my 49 from both sides and get that negative 40 is equal to, this is supposed to be a minus sign right here. Or is it? Yes, this was supposed to be a minus sign in the formula in general. That's my bad. I wrote that down wrong. That's my bad. But I get that negative 40 equals negative 56 cosine c. So the cosine of c equals 46 or 40 over 56. Now I want to solve for angle C. I want to find what angles on my unit circle have an x coordinate of 40 over 56. I don't know that off the top of my head, so I have to use my inverse cosine function. So taking arc cosine of both sides, I get that C is equal to the arc cosine of 40 over 56, which when I plug this into my calculator, gets me 44.4 degrees approximately. Once again, this should raise some red flags. Arc cosine only ever gives me one of the solutions. It only gives me the solution that is in the interval 0 to pi. There is probably another solution, and in fact there is. We can see when we sketch this out, we're finding the arc cosine of a positive x coordinate, so we know we're working in quadrant 1. We know that that's not a good, the 44 degrees is about right here. However, I want the angle, the other angle on my unit circle with the same cosine as my angle C right here. I want the other angle with the same cosine. That's 44.4 degrees. Where is that? Well, it's down here in quadrant 4. And how do I solve for that? Well, this is C here. We go down here, we get to negative C, but we don't want negative C. We want an angle between 0 and pi and 2 pi. So we have to add 2 pi to negative C in order to get that coterminal angle. Let's call this C1. C2 then is equal to our negative C, which is negative 44.4 degrees, and then plus 2 pi. But we're not in radians, we're working in degrees. So instead of plus 2 pi, we do plus 360, which gets us 315.6 degrees. Now, if only having one solution for C1 didn't raise flags, this should raise a lot of red flags. What rule have we been using over and over and over in class up to this point? That A plus B plus C was equal to 180 degrees. In other words, the sums of the angles of a triangle always must add up to 180 degrees. And we can never have a negative angle measure. That wouldn't make sense. So we definitely cannot have an angle measure that's greater than 180 because there is no way to make a triangle out of something like that. There's no way to make a triangle with a 315-degree angle when the sums of all the angles is only 180. So we eliminate this extraneous solution right here, not even having to think any harder about the geometry or what the triangle looks like. And we just know that C is equal to 44.4 degrees. Questions on that deduction? Cool. Now that we have our angle C, I'll just label that 44.4 degrees. We can now either continue with the law of cosines if we really wanted to. We could just keep plug in with the 3 different forms of the law of cosines to get angle B and angle A. Or if you're confident that you've used the law of cosines correctly, we can use our work here and to continue moving with the law of sines because we now have an opposing angle side pair. And that's what I'm going to do. So I now know my opposing angle side pair for C. So I know that the sine of 44.4 degrees over the opposite side is 5. Again, it doesn't really matter what angle I solve for here. I'm just going to solve for angle A because why not? So this is equal to the sine of our unknown angle A over 4. Cool. Solving for A, we get that 4 times the sine of 44.4 degrees is equal to 5 times the sine of A. Dividing both sides by 5, we get that the sine of A is equal to 4 sine 44.4 over 5. I don't know what any angle A with that sine, so I have to use my arc sine function to get the A is equal to the inverse sine of 4 sine 44.4 degrees all over 5, which is approximately 34 degrees. Again, you could check your other solution here. However, because we have already determined all of the lengths of the sides, it turns out that the extraneous solution that we will get in quadrant 2 over here is not the solution. You can verify that on your own if you would like. However, that solution would be 180 minus 34 degrees, which is 146 degrees. Which you can just verify with the picture up here. It's pretty clear that angle A is not 146 degrees. Again, my drawing is not entirely to scale, but it's close enough to the point where I know that angle A does not look like that. So I know that A is going to be 34 degrees. That's just doing that check of, okay, which solution am I working with? And now that we have angle A, we have angle C. We can solve for angle B using this fact up here at the top. So 34 degrees plus angle B plus 44.4 degrees is equal to 180 degrees, which solving for B, we get that B is equal to 101.6 degrees. So, and my drawing kind of matches up pretty well actually with these angle measures. Again, nothing is perfectly to scale, but I made sure that this side was a little shorter than this side, was a little shorter than that side, just to make sure that when I got to my doing the law of sines and having to work with inverse functions, I'd be able to pretty easily take the intuitive check of which of my two solutions is it, because it's clearly not the one that's 146 degrees. Questions? There is a module you're going to have to do in ALEKS called area of a triangle. So we're going to do one brief example of how to use those formulas for area of a triangle. I'm not going to motivate why they work because it's not too important to this class, but you will need to use these when you are completing your ALEKS. So, and they're good, they're just good formulas to have. They're good to know of, okay, how using trig can I find the area of a triangle? Using these three things when I maybe don't know my height and my base, etc. When I can't use 1/2 base times height, how can I use trig? So let's try using one of these in practice, because I want to find the area of this triangle described below that's drawn pretty closely to scale. So I need to pick one of these three formulas that has the three pieces of information I know. There isn't one yet, because if you'll notice, every single one of them requires two side lengths, and I only have one side length, so I need to find another side length before I can even consider what to do with this. In order to do that, I noticed that I do have an opposing angle side pair that I could work with, so I could potentially use the law of sines. I'm going to do that. So I know that the sine of 120 degrees over its opposing side of 7 is equal to the sine of 45 degrees over its opposing side. We don't know what it is. Let's just call it B for now, because it's opposite of angle B. Sine of 120 is √3 over 2, just using my unit circle knowledge. Sine of 45 is √2 over 2. Then solving for B, we get that √3 over 2B is equal to 7 times the √2 over 2. Solving for B, we get that B is equal to 14 times the square root of 2 over 2 times the square root of 3, which equals 7 √2 over √3, which then rationalizing the denominator is equal to 7 √6 over 3. And we've seen this triangle before, actually. Well, that side length at least, so we're going to use that piece of information we knew. Okay, we have that. So I now know sides A and B. So I think I'm going to want to use this formula. However, I also need the sine of angle C, and I don't have angle C yet. How do I get angle C? Well, I know that 180 degrees is equal to 120 degrees plus 45 degrees plus C. Therefore, subtracting 120 plus 45 from both sides, I get that C is just equal to 15 degrees. Now that I've almost entirely solved this triangle, I'm able to use the area formula. And you will have to do that sometimes. Sometimes you'll be able to just use the formula right off the bat. You're just perfectly given the right information. Sometimes you'll need to do a little extra work. This was one of the cases you needed to do a little bit of extra work. So solving for the area, we get that the area is equal to 1/2 times side A, which is 7, times side B, which is 7 √6 over 3, times the sine of 15 degrees. Don't expect you to do any of this by hand, so just plug this into your calculator and you get it's about 5.177. And that's your final answer. If it asks for units or gives you a particular unit on the side length, include units. If not, that's acceptable. Questions on area of a triangle? Again, you don't need to know why these work. You don't need to understand the mechanics behind them. You just need to know how to solve a triangle and how to use these formulas, and you should be good to go. Okay, let's do a little bit of a summary of the 4 kinds of triangles we have approached so far. Angle, angle, side, angle, side, angle, side, angle, side, and side, side, side. And we want to think about, just in general, which triangles will use which rule. Well, First, let's think about which triangle is which. This triangle right here, we know an angle and then walking around another angle and a side. So this is an angle, angle, side. How did we solve this one? Well, we knew two angles right off the bat. So we knew we could solve for our third angle. So we used the law A plus B plus C equal to 180 degrees. If you remember, we needed to do that in order to do the law of sines to solve for one of our side lengths. Then, once we did that, we had our opposing angle side pair and we had another angle side pair when we solved for angle B. So we just finished this problem with the law of sines. We had to use the law of sines twice here, but the only two tools you'll need for angle, angle, sides are the sum of the angles summed to 180 degrees, and you'll need to know the law of sines. Okay, what about the next triangle? We have an angle here, and then we know the side between them, and then another angle. This is angle, side between angle. Okay, what did we do here? Well, remember, we didn't have any opposing angle side pairs start here. We knew angle A, but not side A. We knew angle C, but not side C. We knew side B, but not angle B. So what did we before we did anything else here, we had to start by solving for angle B to get us an opposing angle side pair. So we did that. And then again, this was one of the nice ones where all we needed was just to go ahead with the law of sines. Cool. These two top ones are the nicest. Angle, angle, side, and angle, side, angle. They only require the law of sines and that knowledge of the sum of degrees of angles. We don't even have to bother with the law of cosines. We don't have to think about, oh no, what if there's multiple solutions? Because that never comes up. We just need to use those two pieces of information. What about these two on the bottom? This one, we know a side length, an angle, and a side. We know the angle between the two sides, so it is a side, angle, side. How did we do this one? Well, we didn't have any opposing angle side pairs, and we didn't know enough angles to solve for the angles to get an angle side pair. So we had to use the law of cosines. And we did this to solve for a side length. We did this to solve for this side length right here, which then we used law of sines, which is entirely optional. Like I said, we could have just kept plowing ahead with the law of cosines. However, most people favor law of sines. It's a little easier to work with. It's a little less ugly and complicated to look at, and it's easier to remember. So you could just use law of cosines, but you can also use law of sines. Okay, now what about this one? Side, side, side. We know all three sides, pretty self-explanatory. How did we solve this one? Well, we didn't know any angles. We couldn't solve for any angles. So in order to do that, we had to use the law of sines, or cosines, my bad, in order to solve for an angle. Then once we had that, we were able to use the law of sines to finish off the triangle. And all of these also include the A plus B plus C equals 180 to get the measure of our final angle. Questions on any of these four? Now, there are two types of triangles left that we have not yet approached. These are angle, 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 and side, side angle. We'll see some side, side angles on the next slide. However, just to address angle, angle, angle for a minute, we will never, ever, ever, ever have to solve an angle, angle, angle triangle, and that's because it's physically impossible. If you think about, it's easier if you had one, but think about drawing a triangle, any triangle, and all you know are its angle measures. It could be itty, itty, bitty, or you could blow it up to be much, much, much larger. So like, here's some triangle, its angles are fixed, cool. I could blow it up to be any size I wanted it to be. It still has the same angle measures, but the lengths of the sides are changing. So there is no way to ever solve an angle, angle, angle triangle. So we'll never have to worry about those. Great. All that leaves is side, side angles, which have a complication that the rest of them don't, which is what we are going to address now. So let's do a couple examples of these and then we'll be done for the day. I think I just have 2 examples. Yup. Cool. So I want to solve this triangle here, where angle B is equal to 30 degrees. Or side B is equal to 1, and side C is equal to 4. Okay. With this one, I do actually have an opposing angle side pair. So I don't have to think about the law of cosines yet. I can just use the law of sines. So which ratio am I going to use? I know the sine of B and the length of side B. And what else do I know something about? I know side C. So I'm going to use this to solve for angle C. Plugging my values in, I get that the sine of 30 degrees over side B is 1 equals sine of angle C all over 4. I know the sine of 30 degrees, it's a special angle on my unit circle. Sine of 30 degrees is 1/2. So I know that 1/2 equals sine of C over 4. So the sine of C equals 2. 2 is not a nice y coordinate I know on my unit circle. So I have to use my inverse trig functions in order to solve for C. So I know that C, or one of the solutions to C at least, is the inverse sine of 2. Normally I would say plug this in your calculator to figure out what it is, but if you haven't already plugged this in your calculator, this should raise a red flag. Remember, this right here is a y coordinate. It is an abyssa on the unit circle. So we're looking for an angle C whose y coordinate on the unit circle is 2. The unit circle whose radius is 1. There is no solution to this. If you plug this into your calculator, you should get an error message, and that is because there is no angle with a sine greater than 1. This is not because it is a side-side angle triangle. This is just the nature of the dimensions of the triangle. I gave you a triangle up here that does not exist, and that happens sometimes. And you can kind of, if you want to think about what the heck happened, you can kind of geometrically imagine what's going on here. So let me draw my own triangle. Here I have an angle B. I have my side C equals 4. Here is my angle B here. I know it's 30 degrees. And here is my side length A over here. I don't know angle A, but I know that this side length is 1. What happens here is this side length 1, if you think about it rotating around back and forth, it's too short. It's never going to be able to reach this guy up here. That's not a great color. Let's extend that in pink. Why not? So we don't know what the length of A is yet. That's not determined. But we do know that this little side B here that is length 1 eventually has to cross side A at one point. But this angle is too big and this side length is too small. So geometrically, this triangle just does not exist. There's no solution. This triangle does not exist. And again, that is not because I gave you a side-side angle triangle. This is just because I gave you a triangle with dimensions. It doesn't exist. It's like if I gave you a triangle whose angle measures sum to greater than 180 degrees, or for example, if you had a triangle with a side length of 4 here and a side length of 5 here and a side length of like 27 down here, there will never be a way to expand that 4 and that 5 to get to 27. So there are triangles that don't exist. There are times where you will be given 3 dimensions where you get an error somewhere. And that's not because you did your math wrong. There are triangles that don't exist. So keep an eye out for these. Okay. Now that that's out of the way, let's do a real example of a side-side angle triangle, and then we will be done for today. And we will actually be done working on triangles like this and moving on to something called vectors next time. So anyways, I want to solve this triangle where I have my angle A being 30 degrees. Side A is 3 and side C is 4. Cool. Again, I get to use the law of sines. I know an angle and I know the side length opposite that angle. So I can use the law of sines to start here. So because my opposite angle side pair is A and side A, I'm going to use the sine of 30 degrees over 3 is equal to, I know side C, so I want to find angle C. Solving this, I know that the sine of 30 degrees, excuse me, is 1/2. So I get that 1/6 equals sine of c over 4. So sine of c is equal to 2/3. This is a much better value for sine. It's not greater than 1, and it is greater than -1. So we know that this is a legal angle we are looking at here. But again, it's not a nice one on my unit circle. It's not one I recognize. So I have to use my inverse sine function. C equals the inverse sine of 2/3, which when I plug this into my calculator in degree mode is about 42 degrees. Okay, now, once again, we worked with a function that has a restricted domain, therefore its inverse has a restricted range. So we need to think about what the other solution, what other angle C has a sine of 2/3. To do that, we can draw a picture. I know that C is about 42 degrees, so C is about right here between 0 and 90. Now, I want the other angle between 0 and 360 degrees that also has a sine of 42 degrees. Sine is determined by the y-coordinate. So I have this y-coordinate here. I want the other angle here. Now, remember, these two have the same reference angle, so that's C, that's C. So let's call this C1 and call this guy over here C2. How do I find C2? Well, C2 is just 180 degrees minus the reference angle, which is just C. So C2 is equal to 180, just this flat line right here, minus the inverse sine of 2/3. In other words, just minus 42 degrees, which is equal to 138 degrees. Now, are there any red flags yet that there's only going to be one of these two answers? Nope. I think 42 degrees is less than 180, 138 is less than 180. So these are both legal in that sense. I'm not going to think about the geometric sense quite yet, but it turns out both of these are actually legal in the geometric sense as well. And that's because we don't have our third side length determined. And we'll see why visually in a minute. But let's just keep going, solve our two different potential triangles. So I now have my angle C. What do I do with it? Well, I can use that to solve for angle B because I know angle A and angle C. So, but there's going to be two different potential measures for angle B because, again, I have two different potential measures for angle C. Let's call them B1 and B2. So B1 is equal to 180 degrees minus 30 degrees minus 42 degrees. That's what we got for C1, which is equal to 12. No, that one's not equal to 12. Shoot, that one's equal to 108. The other one, though, where B2 is equal to 180 degrees minus 30 degrees minus 138 degrees, that one is equal to 12 degrees. So we also have two possibilities for B. Again, both of them make sense. 108-degree angle is fine at this point. A 12-degree angle is fine. C1 plus B1 plus A is 180. C2 plus B2 plus A is 180. We're still good. No big red flags. So let's finish out our problem to solve for sides B1 and B2. And how will we do that? Well, we know angles B1 and B2, and we have an opposing pair of known side lengths and angles. Let's use the law of sines. So the sine of 108 over B1 is equal to, let's use the sine of 30. Let's use our angle A side A pair over 3. And then I'd go through the algebra again, but we're running a little short on time. So just do the algebra like you normally would. We get that B1 is equal to 5.7. Similarly, the sine of 12 over B2 equals the sine of 30 over 3. Same thing, just using my different angle B1 and B2 for corresponding sides B1 and B2. Plugging this into my calculator and solving for B2, I get that B2 is 1.2. Cool. So I have two different solutions to this triangle, and it turns out that both of them work. And let's see why. Let's pretty carefully draw what's going on here. Let's try to draw both of these triangles. So I know that no matter what, C is equal to 4. A is going to be equal to 3. And this angle here, and I'm going to draw this line really long, is equal to 30 degrees. Okay, I do not know the length. I do know the length of this side, but I do not know the length of this side here, and I do not know this angle, and I don't know the angle made up here. So we can see right here, we have this triangle. And this works out. This is where we had about 138 degree angle here and our 12 degree angle here. So this actually should probably look a little bit more like this, where that's 12 degrees, that's 30, and this is 138. However, this 12 degree and that 138 degree angle were not fixed right off the bat. Is there another way I could possibly draw this triangle? And the answer to that is yes. So let's see what that looks like. We keep our 30 degree angle down here. We keep this guy right here being length 4. And this guy still has to be length 3 down here. However, what if we keep it length 3, but it gets rotated out this way? Then this angle is a little bit bigger, and that's our angle B. That's when B becomes 108 degrees, and then C up here is 42. So we can think about our side length B here as being kind of a pivot. It can be going inwards like this, or we'll always be able to rotate it and flick it out. Also, still having it intersect side C, still having A being 30 degrees, side A being 3, and side C being 4. However, it's a different triangle. So we have the one that looks like this right here. And we also have the one where side B is flicked out, kind of flicked out from where it was, still intersects side B, whose length is not predetermined, which is why we're allowed to do that, because we don't know the length of this guy from the start, and then is just also makes a legal triangle. And the reason we can do this is because the side lengths are not predetermined. Unlike the side angle side where we had that potential of maybe there's 2 solutions, the lengths of the 3 sides were never ambiguous. We never had multiple solutions for the lengths of the sides. But here, because we do have multiple solutions for the length of one of the sides, i.e. being B1 and B2, this could possibly have 2 solutions. In fact, side-side angle is the only scenario with 2 solutions. In fact, side-side angles will have 2 solutions in every single case, except A, like the case above where we had no solutions just because the triangle didn't exist, or B, when we're talking about a right triangle, this kind of triangle will only have 1 solution, but you won't be given right triangles and asked to solve them this way, because if you're given a right triangle, you just get to use the Pythagorean theorem. But these kinds of triangles, you'll have to do a check, but they will always have 2 solutions. None of the other kinds of triangles are. So if you are able to recognize what kind of triangle you're working with on a homework or an exam, if you're able to recognize, hey, I know this is a side-side angle triangle, you know both of the solutions are going to work. I would always still suggest drawing a picture to mentally check that in your brain of, yep, there are 2 different possible triangles. If we had more time in a classroom, we would be taking a ruler and a protractor and very precisely drawing these 2 triangles just to demonstrate why it works. I know my very crummy drawings here don't work, but if you want to confirm this for yourself, it's a helpful exercise. But just know this is the only scenario where that will happen. All other kinds of triangles, side, 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 angle, angle, and angle, angle, side, those will all have 1 or no solutions. And you will never be asked to solve an angle, angle, angle triangle. Questions on any of these types of triangles, identifying them, solving them, etc. Okay, if there's no questions, that is all the material I have for today. Next time we will be moving on to vectors. We're in the home stretch of the semester. We're doing vectors and then a teeny bit more graphing with something called polar coordinates, and that is it. You'll probably see in your course packet we're really close to the end. So, home stretch, we're almost there. I'm going to log off the Zoom meeting and immediately post the homework once I am logged off. But if anyone has any questions, feel free to stick around. Otherwise, I will see you all tomorrow and keep up the great work.